All right, let's dive deep into the belly of the beast, the Python interpreter itself. We're going to follow the entire journey of your code, starting from that simple .py file all the way to what your computer actually does with it. This is all about understanding what CPython, the engine behind pretty much all the Python code out there, is really doing. Let's get into it.
I mean, seriously, have you ever stopped to think about it? It kind of feels like magic. You write this simple, super readable text, you hit enter, and poof, stuff happens. But it's not magic, not at all. There's this really fascinating, very specific mechanical process chugging away under the hood. And understanding that process, that engine, is honestly the key to writing better, faster, and smarter Python.
Okay, so first things first, let's clear up a huge misconception right out of the gate. A lot of folks think that your Python code gets compiled all the way down into the ones and zeros that your CPU runs directly, like a C or C++ program. But for CPython, that's just not how it works. The reality is, CPython is a program itself and it's written in C, and your Python script, your code is just data that you're feeding into that C program.
This is a really crucial mental shift. You have to stop thinking of your .py file as a standalone program. Instead, think of CPython as this sophisticated machine, and your .py file is just the set of instructions, the blueprint you hand over to it. The CPU is running the CPython machine, and the CPython machine is the one running your script. Your Python code itself never actually becomes that native machine code.
So, if our script is just a blueprint, how does the CPython engine actually read it and turn it into action? Well, it's a multi-stage journey that all starts with turning our nice, human-readable code into something that the engine can work with way more efficiently. Here's the high-level roadmap of that journey. First, CPython reads your file and parses it, turning your code into a tree-like structure called an abstract syntax tree, or AST. It's just a way of organizing the code logically. Then, it compiles that tree. But, and this is key, it doesn't compile the machine code. It compiles to a special set of instructions called Python bytecode. And finally, the interpreter's main evaluation loop takes that bytecode and executes it one instruction at a time.
So what in the world is this bytecode? The absolute best way to think about it is as the unique assembly language built specifically for the Python virtual machine. It's a lower-level, platform-independent version of your code, totally custom-made to be executed by the CPython interpreter and nothing else.
And check this out. This is a perfect example of that translation. One simple line, print, hello world, actually becomes two bytecode instructions. The first one, load const, literally just loads the constant string hello world onto an internal memory stack. Then, the next instruction, print expr, pops that value off the stack and takes care of printing it. Every single thing you do in Python gets broken down into these simple, discrete little steps.
All right, so we've got our bytecode instructions. Now we need something that can actually understand them and run them. And for that, we have to enter the very heart of CPython, the interpreter loop.
Conceptually, it's actually incredibly simple. The interpreter is basically just one giant while loop written in C. And in every single turn of that loop, it does three things. It fetches the next bytecode instruction, it decodes that instruction to figure out what it's supposed to do, and then it executes the C code that actually performs that action, like loading a number or adding two things together. Fetch, decode, execute, over and over and over, until there are no more instructions.
Okay, that makes sense for a simple script that just runs from top to bottom. But let's be real, our programs are full of functions. How does the interpreter handle jumping in and out of those? Well, that requires a little bit more machinery.
So when Python first compiles your code, it creates something called a pycode object for every single function you've defined. You can think of this as the permanent reusable recipe for that function. It holds all the bytecode for the function, any constants it needs, and a bunch of other metadata. The important thing is, this object is created only once.
Now, here's where it gets really interesting. That pycode object is the recipe, but every single time you call that function, CPython creates a brand new, fresh pyframe object. This is like a temporary private workspace just for that one specific call. It's where it keeps track of all the local variables for that call, it has its own little evaluation stack, and crucially, it knows which bytecode instruction it's supposed to execute next. So if you call the same function twice, they both share that one pycode object recipe, but they each get their own separate disposable pyframe object workspace.
All right, so we've got a handle on how a single flow of execution works. But what happens when we try to do multiple things at once, using threads? Well, this brings us to one of the most famous, and maybe infamous, features of CPython, the GIL.
This is the million-dollar question for so many Python developers. Python's threads are the real deal. They're actual operating system threads. On a modern multi-core machine, you'd think they should be able to run in true parallel. And yet, if you take a really heavy calculation and try to split it across 4 threads, you often see 0 speedup. Why is that? The answer, in 3 letters, is the GIL, the Global Interpreter Lock.
So what is it? The GIL is a single global lock, a mutex. Before any thread is allowed to execute even a single Python bytecode instruction, it first has to acquire this lock. And here's the kicker. Only one thread can hold that lock at any given time. This means that even if you have 8 cores and 8 threads, only one of them is actually running your Python code at any single moment. The GIL effectively forces all your threads to run one at a time.
But, and this is a huge but, there's a crucial detail. The GIL behaves differently depending on what your thread is doing. For I/O-bound tasks, like when your code is just waiting for a network request to finish or doing a time.sleep, the thread actually releases the GIL. This is fantastic. It lets another thread grab the lock and do useful work while the first one is just sitting around waiting. This is how you get concurrency for I/O. But for CPU-bound tasks, like a heavy math loop, the running thread holds on to the GIL for dear life. It doesn't release it, which means no other thread gets a chance to run. And that is why you don't get true parallelism for CPU-heavy work in threads.
So, wow. We've gone all the way from a simple script, down into bytecode, through the interpreter loop, and into the weeds of the GIL. Let's pull back up and connect all these technical details back to how you and I actually write code every day.
If you walk away remembering nothing else, please remember these 3 things. Number 1, CPython is a C program, and your Python script is just data it operates on. 2, the GIL means only one thread can run Python bytecode at a time, period. And 3, the whole reason threading is useful is because threads release that GIL whenever they're blocked waiting for I/O.
And that knowledge leads directly to some very practical advice. If your task involves a lot of waiting, you're hitting APIs, downloading files, talking to a database, then yes, absolutely use the threading module. It's perfect for that. But if you need to really crunch numbers and use all of your CPU cores at once, you have to get around the GIL. And the standard way to do that is with the multiprocessing module, which spins up whole new processes, each with its own interpreter and, you guessed it, its own GIL.
So there you have it, the whole journey from pythonscript.py to actual execution. It's not magic, it's a system. A system with very specific rules and behaviors. But now you know those rules. Understanding that your code is just data for this engine and understanding the rules of that engine's lock, that gives you the power to make way smarter decisions about how you structure your programs for real-world performance. Thanks for diving in with me.